So first of all, thanks to the organizers for inviting me. This has been just an incredibly interesting, fun meeting. It looks like Matthew's gone to the bathroom. I was going to talk about him. But okay, quick. No, I was just going to say, just looking back, to 2006, 2007, me and Matthew and Dunk, were on this original Lorimer burst paper, and Dunk kind of never lost faith. And I think both me and Matthew had moments where we were like, Dunk, I don't think this is real. And we were totally wrong, and it's totally nice to be proven wrong. I couldn't ever be happier about being proven wrong about anything, and it's just amazing to see what's happened in the field. So I'm tasked with talking about the future of FRB observations in 15 minutes, and I'd like to thank Jason for giving an excellent overview talk, and I'm going to hit on a lot of the same themes, but in a little bit more detail than what Jason hit on. First of all, I'm just going to talk about radio observations, and I thought I'd start just with the basics, right? So let's think about the things that we want to observe about FRBs, and then I'd like to talk about what we want in a radio telescope to do that, how our current facilities compare, and how we might want to design facilities for the future to measure all the things that we want to measure about fast radio bursts. And so I'm not going to step through these word by word. This is kind of boring, but this is a summary of all the types of things we'd like to characterize about FRBs. Some of these are simple physical measurements, and some of these are inferred things like periodicities on short time scales, long time scales, polarizations, pulse widths, both spectrums and also frequency structure. And so if we just look at like the kind of radio qualities we would want, right, from a radio observatory, lots of these are obvious. I apologize to the radio astronomers. This is sort of very basic stuff. But just to start from common ground, we want frequencies that are sort of hundreds of megahertz to tens of gigahertz to optimally measure RM, scintillation, scattering. These might look a little bit different, but they basically overlap. If we want to measure short, millisecond to second periodicities, like we might get from a neutron star rotation, obviously we need fast sampling. We want long observations, sort of like hour, 2 hour, 3 hour observations to really get an underlying rotational periodicity. And that's something that we're missing for a lot of these FRBs, and I think is really, really important. And what this means is large fields of view, right? We don't want telescopes where sources are only up for 15 minutes. We need telescopes that can track sources for hours. We also want to discover more long-term periodicities, like the one found, the 16-day periodicity found so far. And for that, we need frequent observations, right? We want high cadence observations like CHIME, and optimally continual observations, right? We want to be on sources all the time. And so this also pushes us towards very large fields of view. We want to characterize spectra. Obviously, that means wide bandwidths or observations at multiple frequencies. We want to get at the frequency structure. Again, wide bandwidths. This is pretty obvious. If we want to study these things, we need fast sampling, we need good polarization calibration, and we need interferometry for locations and distances. And then just a reminder, we also have this big old radiometer equation, which of course, all of these things we're going to do better if we are more sensitive, right? The more photons we get, the better we're going to do all of these things. And so this pushes us towards large collecting areas and large bandwidths. Okay, so this is a very basic summary of our needs. There are other considerations, of course. One thing I just wanted to throw up here really briefly is the discussion about RFI, because we really haven't hit on it much. RFI is a big problem. It's something we really need to think about when we're planning future arrays. These show the bands that are going to be used by 5G. It's a little bit scary. It's only going to get worse. Vikram and Greg showed this really interesting plot yesterday at their RMS panel presentation on the DSA 2000. These are two dynamic spectra. This is time versus frequency for two different sites they're considering for the DSA. And it's just an example of how two sites that are separated by not that many miles, a few hundred miles, can look quite different in radio frequency interference characterization. This is a problem. With RFI, we might get spurious FRBs, but we also are losing a whole lot of the band, and we really need this band both for radiometer sensitivity and to track spectra and these interesting spectral features. Okay, a couple other considerations. Again, apologies to the radio astronomers, but we all know that if we want to observe a very large field of view, if we want to get a big solid angle, we want a dish with a small collecting area. And so this is the area of an element of an array, or of a single dish for that matter. So Arecibo has a very small solid angle on the sky because it's really big. And we also know that this is proportional to the wavelength squared, or 1 over the frequency squared. So this is an important consideration. This pushes us towards large N, small d arrays. So big arrays made of very small diameter telescopes. And it pushes us towards low frequencies. There may be other reasons to go to high frequencies, but just from the point of view of maximizing our field of view, low frequencies are better. And a word about cost. So the main impediment to these large N small d arrays, of course, for years has just been the cost and combining beams, combining signals from multiple beams. But Moore's law tells us that this cost is, it's going to decrease every year. This is becoming very computationally feasible, and we've seen that with upcoming arrays and with arrays that are planned for the next decade. Okay, so this is really super wordy, but basically we want large N, small d arrays, we want big bandwidth, fast sampling. We want to look at the lowest frequencies we can to get the large fields of view, but of course we still want to measure interesting things that we want to measure about our populations. So what is the population we want to see, and how do we arrive, at the number of dishes, area, and frequency for a particular radio telescope we might want to design? And so there's 2 other really important considerations that have been discussed already at this meeting that are just super important to making these kind of decisions. The first one is this source count index, right? So how does the number of sources we detect vary with flux, with brightness? And this has, of course, been really important going back to the days of, whoops, why don't I use this instead of tripping over it? Going back to the days of gamma ray bursts and discriminating between different models for GRBs. So some of these gamma ray bursts follow a Euclidean distribution, where this index here is minus 1.5, some of them don't. That points to different cosmology, different evolutionary histories. This is a really important quantity that we really haven't characterized well for FRBs so far. There have been attempts to do that. This is an example of one paper where they took a bunch of detections and upper limits. The number that they derive is quite a flat source count distribution. So this is flatter than Euclidean. In this case, you're going to have a lot of bright sources, not a lot of faint sources, and your best design bet would be to maximize solid angle at the expense of collecting area, right, if this is what your source count distribution looks like. However, other estimates are much, much steeper. In this case, you're going to have a bunch of faint sources, and you really want to maximize collecting area instead of solid angle, right? And so you have these competing demands. This is a really nice plot which shows this, and I'm sorry about the different, I called it gamma before, it's alpha on here, but this is the source count distribution index going from 0 to 2.5. So you can see if you have something very flat like this, then you're going to do better with something like ASCAP. You don't have a lot of collecting area, but you have a wide field of view. If you get to very steep indices over here, then you want a lot of collecting area, a lot of sensitivity, and you don't care so much about field of view. So the VLA will do better over here. The DSA 2000 is a nice design because it's something that sort of bridges the gap between those 2 types of instruments. The dishes are fairly large, so you have a good amount of collecting area, and you also have a good field of view, and so it's not super sensitive to this source count index. Okay. Another huge consideration is, of course, the spectra of FRBs, which is also not very well defined at all. There's a couple good reasons for this. The first one is that it's really complicated to calculate spectral indices for repeaters such as this. It's also complicated even for the non-repeaters due to scintillation. So this shows a lot of scintillation within the band. This one's really faint. So how do you get it? I do not know it's scintillation. Yeah, I don't know it's scintillation. Looks like scintillation, but yeah, I don't know. Yeah, so I guess the summary is it's complicated, regardless of what it is. So this paper this is actually the same data as in this plot, but they took 25 different FRBs, plotted their spectra, and fit basically a composite spectral index to all of them. They arrived at something which looks like minus 1.4. This is kind of pulsary. However, even though this would kind of push us to look at low frequencies, we're missing out a lot of valuable discovery space. So this shows the breakthrough FRBs, the pulses from the repeater, detected at 5 gigahertz. And so we know that some are also very, very bright at high frequencies. Okay, so the summary here is that we really don't understand the source count index so far. We don't have a good handle on how the number of FRBs depends on flux. We really don't have a good handle on spectra, but we do know we want wide field of views, large bandwidths, all sky all the time. So this plot, it's a really nice plot made by Sarah Brooks-Blar. I think Casey showed this in his talk as well. This is localization on this axis, and this shows FRB detections per year, and current FRB surveys are shown here. These are the assumptions that Sarah used for this plot. And I asked her, can you send me a couple plots where like some of these are tweaked and we can see how this looks if we like slightly change the assumptions. So in this one, she's assuming that this source count index goes between minus 1.5 and minus 0.5. If we say, let's assume that that's a very shallow index, right? So we have a lot of bright FRBs, not so many faint FRBs. You can see that pushes the predicted rates with CHIME way up. It pushes the predicted rates with telescopes that have, much larger collecting areas and smaller fields of view way down. And so this is meant to illustrate that through all of these surveys, we're really going to get population statistics that can help us constrain things like this source count index. Okay. This one's pretty obvious, but if you do something else crazy, like you say spectral indices are actually positive and they get brighter at higher frequencies, then of course, these VLA surveys are going to have much higher detection rates. And so the point is just to illustrate that, in a few years, with all the FRBs detected by these different surveys, we really will be able to place constraints on these different, very important properties of the population. Another thing I just wanted to point out with this plot is that right now we kind of have like two different types of instruments, right? So we have instruments like CHIME, which can do population statistics and sort of identify individual FRBs. And then we have other instruments like the Real Fast Survey that Casey talked about, which can do precision localization, right? So you really need to get below this sort of arc-second level to be able to localize an FRB to a galaxy. Okay, and so we have these two different types of instruments right now. And what we really want to do going forward is have instruments which can do both, right? So we want to be able to both localize an FRB to a galaxy and discover it at the same time. And this is really the only way forward. I mean, Jason mentioned this as well, but the discovery rate is going to be just ballooning over the next decade. And we really need to have instruments that can do both things at the same time. Unfortunately, there are instruments either in operation, like HIRAX. It's not fully in operation, but it's built in South Africa and the DSA, which, as you've heard a lot about it, but this is a submission to the RMS panel in the US, and it'll probably be built out in Nevada or California, and CHORD, which is the next generation CHIME, that'll do both of these things. So it can do population statistics and cosmology at the same time. Okay, so just a little bit about these next generation arrays. If you look at the properties of these arrays, the DSA 2000 will have a spatial resolution of a few arc seconds. CHORD will do better than that. It'll get to milli-arc seconds because it'll have outrigger stations. So it'll use CHIME, and then there'll be a bunch of outriggers. Otherwise, the specs of these are fairly similar. This one would be a little bit more sensitive than CHORD. It'll have a little bit more total collecting area. I'm running out of time, so let me just go through this a little more quickly. I'm not going to talk about this. Okay. So that's kind of the state of play right now. I think, though, looking forward, like kind of a decade down the line, what we really want are all-sky telescopes. We want telescopes that are observing as much of the sky as possible, basically all the time. And I think if we can do that, we're going to make just humongous progress in identifying counterparts, in measuring periodicities, and sussing out any sort of other kinds of timescales or quasi-periodicities in the emission. Two telescopes that have been proposed that will do this are PUMA, and this was a submission to the US Decadal Survey. There's also something that I'm calling the WFBT, the Wide Field Burst Telescope. This is a paper by Jeff Peterson. This is an aperture array. So these are basically radio tiles, like honeycomb radio tiles. This is obviously a dish array. Jeff carries out some nice calculations in his paper looking at the scientific payout versus cost of these arrays. And he finds that if this source count index is fairly high, so if you have a lot of bright sources and not so many faint ones, you do better with an aperture array like this. Once this gets steep and you want to detect a bunch of faint sources, then you do better with a dish array. And the reason for this is that these aperture arrays are just really expensive computationally. So if you need a ton of collecting area to detect very faint sources, then that really pushes you towards these dish arrays. But these are some of the things that I think are on the horizon and really are the way to go, when we're talking about like decades in the future. One thing I just wanted to touch on really briefly is there a role for single dishes? If you look at this plot, it kind of looks pretty dismal. If you look at, GBT and perks, they're kind of way up here, low event rates, poor localization. There obviously is still an important role. I think we all know that from the Arecibo studies of the repeater. And so we've seen that Arecibo, for instance, has detected and characterized the very faintest burst from Arecibo. That's super important for the emission mechanism. These are two plots from two commensal surveys at Arecibo and Green Bank. So one's called Alpha Burst, the other one is called Green Burst. And so these things are running all the time on the Arecibo and Green Bank telescopes. Well, this one's really running all the time. It takes data with the L-band receiver no matter what's going on. This one is only running when the alpha receiver is in focus. And so you can see this purple region is the region to which this alpha burst survey is sensitive, and it probes the very faintest fluences. These are the known FRB population here. This green burst survey, this is days to detection versus this source count index. And you can see that it's very, very sensitive to this source count index. And that's because we're peering very, very deep. We're looking to very high redshifts to very faint FRBs. And so this is one of the best ways to really place constraints on this source count index. It's a little sad. We've been doing it for 110 days now, and we haven't detected anything. But we can place very good constraints on alpha. It comes out to be about like 0.8, 0.9. This is using other constraints as well. So we can get useful science out of the fact that we haven't made a detection yet. It would be better to see something. But these single dish telescopes that look to very high redshifts and can detect very faint sources are still really important. And finally, this is my last slide. I just wanted to talk a little bit also about commensal observations. So a WVU undergraduate named Ben Gregg is writing a paper up on using the 20-meter telescope at Green Bank. So this is a small telescope. But what he did is he's co-observed 557 Swift pointings. So got the Swift operating plan, and for all the Swift pointings, he's just tracked those pointings with the 20-meter dish. And the reason is obviously that if we detect an FRB, we would have high energy data right at that same position, and we could place very good constraints on the presence of gamma ray photons. Obviously, there's been no detection. This is the sky coverage. But I think these kind of things are really important. Just one detection could be super constraining. And I encourage those of you who might have small radio telescopes that could do this kind of thing to get on board with commensal observations. You could only detect very bright FRBs, obviously, but the gamma ray emission is expected to be faint. So probably the FRBs would be really bright anyway if you're going to detect coincident gamma ray emission. OK, so maybe I will just leave this up. My last bullet point is really similar to the one that Jason made at the end of his talk. And I will take questions. Thank you. Sorry if I got a little over.